As I said in the previous video, we're going to prove Rolle's theorem, so then we can use it to prove the mean value theorem. And something very interesting that we will see later is that actually Rolle's theorem and the mean value theorem are equivalent. They just mean the same thing. Okay, so what does this theorem says? Well, it tells me that if I know that a function f is continuous on the closed interval ab, f is differentiable in the open interval ab, and I know that f of a is equal to f of b, then there exists a point c between a and b such that f prime of c is equal to 0. So if you look at it, the first two conditions are the same as the conditions that we had in the mean value theorem. So, okay, so we have this theorem and let's try to make sense of it. So here we have some typical functions that satisfy these three hypotheses. So we had this one, well, it goes up and then it goes down. Then this one goes up, down, and then up again. We have a constant function. These are some typical scenarios that we can have. And if you see here, well, the points where the derivative is 0 corresponds to points where the tangent line to the curve is horizontal. And if you see here, it seems that those happen precisely where we have maximum or a minimum. And that is the idea that we're going to use here in this proof. You will see, as I said before, that to prove Rolle's theorem, we're going to combine the extreme value theorem and the local extreme value theorem, because what we're going to do is we're going to show that under these conditions, our function would have maximum or minimum, and for some of those points, we can actually say that my derivative has to be 0 using the local extreme value theorem. So let's get started. Before we do that, let's remember some definitions. We're going to say that f has a local maximum at c if f of c is greater than or equal to f of x for all x in some open interval containing c, and f has a local minimum at c if f of c is less than or equal to f of x for all x in some open interval containing c. And then the extreme value theorem tells us that if f is continuous on a closed and bounded interval ab, then f attains both a maximum and a minimum value in that interval. And the local extreme value theorem tells me that if f has a local maximum or minimum at c, then f prime of c is equal to 0 or f prime of c does not exist. So that's how we're going to combine these two theorems. So how do we do this? Well, we know that my function f is continuous on the closed interval ab. So by the extreme value theorem, f attains a maximum and a minimum on the closed interval a, b. Okay, and now we're going to have two cases. First case, that f attains a maximum or a minimum at some point c strictly between a and b. So c is in the open interval ab. If this happens, then, well, if we have a maximum, that maximum would be a local maximum, or if we have a minimum, that would also be a local minimum. So a global maximum or a global minimum, they're also local. So, okay, so we have that as a local maximum or a local minimum. Okay, but then the extreme value theorem tells me that then the derivative at c has to be equal to 0 or it doesn't exist. But you see, c is inside the open interval ab, which means that my function is differentiable at c. So that will tell me that then f prime of c has to be 0 because we know it exists. And then we have another case. What if both the maximum and the minimum happen at the end points? Well, we know that f of a is equal to f of b. If both the maximum and the minimum happen at the end points, that means that the maximum and the minimum are equal to each other. So the function has to be constant. But you see, if my function is constant, then the derivative of x is equal to 0 for any x in the interval. I'm sure you believe me, but if not, then write a proof using just the definition of derivative and you will see. For any constant function, we know that the derivative is 0. Okay, Now this happens for any point x in the open interval AB. So, well, that tells me that in either case I can always find a point C in the open interval AB such that the derivative of f at C is equal to 0, which is exactly what we wanted to prove. We already know the proof of Rolle's theorem, but now I want to highlight something very important, and is that all the hypotheses of the theorem are necessary. You see, if f of A is not equal to f of B, we could have this scenario, and you see that there is no point where we have a horizontal tangent line, so we don't get the conclusion of the Rolle's theorem. If we know that f of A is equal to f of B, but f is not continuous on the closed interval, we could end up with a picture like this one. And again, there is no point in the open interval AB such that the derivative is 0. So again, we cannot reach the conclusion of Rolle's theorem. Or we can have that f of A is equal to f of B, that a function is continuous on the closed interval AB, but f fails to be differentiable, like in this case. And again, because f was not differentiable in the open interval AB, then we cannot guarantee that we have a point for which the function has derivative equal to 0. There is no horizontal tangent line in this case. So whenever you want to apply Rolle's theorem, it is extremely important that you check that all the hypotheses are satisfied. That a function is continuous on the closed interval AB, differentiable on the open interval AB, and that f of A is equal to f of B.